We will do a review session this Thursday. So another one where we can just kind of chisel through more homework, clear up any ideas. We were really productive last Thursday, so I already feel we're a little bit ahead. So good on us, good on you guys. And then I think we'll do another review the Thursday after, just because we have a final, or a midterm, not a final yet. So a midterm exam, and I like to do yes, no, maybe on that. So the idea is you ask me what's on the exam, and I tell you either yes, no, or maybe, and I try not to fill up the maybe column. So we limit that. So a maybe would be a strong contender, a question that I have used in a midterm before. That's absolutely something that I would ask, but I'm only going to ask you about 4 questions on the midterm. It's not going to be super overboard. If you can do the homework quickly, you'll be on track. So that's where we're going.
How long do you have for the midterm?
What's that?
How long do we have for the midterm?
50 minutes. So that's what the university gives you. I don't get the room for any more. So, 50 minutes. So it's going to be one of those quick things. Can you do easy problems fast? Later on, when we get to the final, I'll give you probably some practice questions for the final so you can build up, so you can kind of see the full coverage of the class, and then I'll pull some questions out of it for the final exam. Maybe alter them a little bit, so it'll give you at least a chance to study for something specific instead of, well, the whole entire class. I can understand that that can be daunting at some times, but you'll get 2 hours on that. So what is the point of a 50-minute midterm? It's really just to motivate you to study. So lots of motivation. So that's the way I see it. So I like that part of it. If you're well practiced, then maybe the nerves don't kick in quite as hard. Let's see. I think what we'll start out with, I think we'll come to a simulation study. I'm just going to pick up from the PowerPoint that I presented on Friday, but I'm just going to show you on the board how all that works. So, and then we're going to do a simulation study. Oh, I see what I'm missing. Does anybody have an adapter, a Mac adapter for HDMI? Nobody? You're awesome.
USB-C root plus epsilon is good.
Yeah, exactly. 2 epsilons.
Oh man,
Yeah. Is that also a mouse?
No.
So I'll give you some definitions first. More days. What I'd like to tell you about is conjugate priors. Give you a definition for that word. It's a class of priors that are commonly used. They're very convenient. You can do all the calculus by hand. If you know the properties of your prior distribution, you'll know all the properties of your posterior distribution. It goes a little bit further than this. I won't say this in this class, that some of the conjugate priors, depending on how you parameterize them, can be optimal in different senses. So maybe I can come up with a prior that gives me point estimators based off of some loss function. We'll get there in chapter 7. So maybe squared error loss or absolute loss. So I come up with an estimator and I measure the deviation from the truth. And in a simulation study, you can concoct that. So I can maybe make us optimal in a variance sense, in an MSE sense, in a bias sense. I could maybe come up with priors that produce intervals that cover at some optimal frequentist rate. So when people say they have something like a 95% confidence interval, the idea is you construct a confidence interval, and if you went out and you collected more data and you applied the same procedure to come up with another interval, we might expect for a 95% confidence interval, it covers the truth 95% of the time. In the examples using normality, they're exact coverage. So in the Bayesian would come up with the exact same interval, and they would have a different interpretation. So we will talk about that when we're carving through this lecture. But my point is that a Bayesian can be optimal in a frequentist sense or a lot of other senses. And the prior is what we tune or we adapt to get different versions of optimality. You can kind of imagine that in one-dimensional settings, you might have a lot of versions of optimality simultaneously, but in high-dimensional settings, you have to choose. So you don't get it all simultaneously. And that's true for all kinds of problems. So what's hard about high-dimensional spaces, and when I say high D, I kind of mean 2. So, because that's where everything kicks in, it's that they're not ordered. So there's no natural ordering to a 2-dimensional space, but in a 1-dimensional space, things are ordered. So we have to kind of get away from, thinking about everything as this natural ordering. High-dimensional spaces, as they get bigger and bigger and bigger, they become even more cumbersome in that the action in the space is very sparse. So as I end up increasing the space bigger and bigger, most of it is empty. And so searching through empty space is hard. You can kind of imagine in a 1-dimensional setting if I'm looking for something, so if I'm searching for a maximum or a minimum or anything, all I have to do is sweep from the left to the right, and eventually I'll find it. And we've all coded up algorithms that do that, and maybe there's fast algorithms where you jump to the right a little bit, and then you jump to the left, and then you jump to the middle point, and then you kind of scan the 2 sides, and things like that. So bisection searches, golden section searches, that sort of stuff. In 2-dimensional settings, that stuff is impossible now. Now it's like, you can't just sweep from the left to the right. You need to somehow scan into that space. So you might go up, down, up, down, up, down, up, down. That might not be the most efficient thing. Or back, forth, back, forth, back, forth. And scan the space, but it takes a long time to do it. Okay, so we're gonna be a little bit optimistic here. We're gonna have lots of properties for free. So just keep in mind if you want to know more about prior distributions, that's where Bayes class would come in. And we'd spend most of the time just talking about that, and then the relevant computations that a Bayesian does. So I'm going to give you the spirit and the idea in this class because this isn't a full-blown Bayes class. I think that this is probably like a 25% Bayes class. It's an inference class. So inference is Bayes. And I want to just point out, it's not just me lopsiding the class. Casella and Berger are Bayesians as well. So at least Casella was. So that's why there's so many of those problems kind of riddled through. So I want us to just think about the properties, and if you like certain techniques more than other techniques, that's up to you. So, but at the end of the day, we're going to analyze all this based off of the properties that we get. So not just philosophies. So let's just start here, conjugate priors. And then we'll move back to our example. So I'm just going to say, again, a posterior distribution, or I'll just tell us what Bayes is. Actually, let's start with Bayes, then we'll jump to conjugate priors. So Bayes' theorem. We looked at this last time on the board. So this was the theorem that followed Bayes' grave. So he passed away. Richard Price shows up, starts looking through his stuff and says, oh, there's some really good ideas here. Let's get these published. And that's what happened. So what Bayes wrote down was this. So the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. And if you know what conditional probability is, this is just a rule of conditional probabilities. Uncontroversial, this is just how you get there. So I want to just explain that we can maybe intuitively understand this rule. So let's just rewrite this. This is the probability of B given A times the probability of A equal to the probability of A given B times the probability of B. And if you know what a joint distribution is, and you can talk about the exchangeability of the events, that the ordering doesn't matter, then this rule makes sense to you. So let's just think about this just a little bit. I guess I said milkshakes and hamburgers last time. Any vegetarians that are going to be offended or grossed out? I've had that happen before. You want broccoli and cheese? Hamburgers? Okay. Flavor of milkshake? Preference? Chocolate. Okay. Chocolate milk cheese. So let's do this. A is equal to buy a hamburger. And I guess we could cover all bases. This is a black bean burger, something like that. So we'll try to keep this inclusive for all of us. So whatever your fancy is, buy a burger. So I'm just going to call this the events. And B is buying a chocolate milkshake. This is obviously almond milk, and my chocolate is carob. So if you've ever had that before, have you guys ever had carob? So we used to grow up with it thinking it was the chocolate alternative. You guys are smart. You'll never learn what that stuff is. So it's not as good. Okay, two events. Buying a burger and buying a chocolate milkshake. So let's just think about what this says right here. So this says these events right here are saying if I buy a burger, so this is the conditional statement, then I'll buy a chocolate shake. So that's how I think about this event right here. Maybe I'll put R's everywhere, so these are all just discrete statements. So that's what this event is, and that's the probability of that statement. This right here is just that I'm going to buy the burger. The event buying a burger. So these events are not independent of each other, they're conditionally independent. So I'm conditioning on one event. So buying the burger, then I buy the chocolate shake. Oh, did I just?
Yeah, that's all.
How about this?
Yeah.
Of course. So all these little easy things that I should be able to get right. They're always the most confusing. Sorry about that, just switch the order there. So that's what this says, and multiplication means and. That's true every single time. And that's pretty easy to kind of convince somebody of. So if I say there's a 50% chance of something, and I'm only going to have a 50% chance of that thing happening in the first place, I multiply those two numbers together and I come up with a quarter. So that's what that means. So anytime you see multiplication, you're thinking the word and. So these aren't independent, they're conditionally independent, and we've conditioned properly. So what does this actually say in this event space? It says, if I buy a burger, let me say it this way. If I buy a burger, then I'm buying a chocolate milkshake, and I'm buying a burger. What did I just say? I'm buying both. So I'm going to buy both of them. Same thing over here. So this one says, if I buy a chocolate milkshake, I'm buying a burger. Good. And I'm buying the chocolate milkshake. So I've said it in a different order, but I've said again at the same time I said I'm buying both. And these are the probabilities of those statements. So that's all Bayes' theorem is. So, and this extends to continuous cases, and there we'd probably need some sort of a proof. Taking limits, making sure we understand the rates of convergence of the numerator and the denominator, and we're just going to skip over that. So if you take a measure theory class, they'll take you through that, and they'll say, maybe Bayes' theorem isn't so obvious in the continuous case. So we need to make sure you think it's obvious by taking you through 10 pages of proofs. So, but it turns out all of this extends for the exact same intuition to continuous spaces. So this is discrete space, here's continuous space. So all these probability rules that we learn apply to discrete stuff and continuous stuff. And it actually works for mixtures of those two things as well. So for continuous space, I can write down something like this. F of B given A times f of A is equal to f of A given B times f of B, where these are mixtures right here. Bless you. I'll also say that if everything was continuous, this is true, and you can reorganize this for whatever version of basis theorem you want, whichever conditional you're flipping. But this is the rule to flip conditionals. You can also apply this when one of these is continuous and one of them is discrete. So you just need to use the right operator and call one continuous and one a probability. So one's a density, one's a probability. And you can mix and match those two things as long as you're using the right operators. So just depending on your version of summing, all of this stuff just kind of applies. And I think that it's pretty intuitive when you just realize this statement right here is just probability of B and A. So that's the joint distribution. And this one over here is the probability of A and B. Now somebody will probably say, oh, do the orders of these things matter? And because I'm able to just exchange them around, I'm making a statement about exchangeability, that I can just exchange those orders of everything as well. And it's not important. If we were studying something like a stochastic process that is run in a particular direction in time, we'd have to be more careful about the ordering of everything. So in a Markov chain, we might have to establish some theory to talk about reversibility of everything. But in the rule that I'm writing down, these are just exchangeable events. So that's basis theorem. So this is how Bayesian used basis theorem. So first, write down the likelihood. And I'll just point out that the likelihood function often looks like something like this. It looks like the joint sampling distribution. And when you write this down, you could be confused and think, what the heck does this mean? I need to think about it being a function of this. So function of theta. And this is also a function of theta. So I'm writing that over on the right-hand side, but I'm keeping sure you remember that whatever this equation is, this is a function of theta. And that's what a likelihood is. That's where some of the confusion comes from. With moving from a sampling distribution to a likelihood, they look the same, but they're not the same. Because the sampling distribution is a function of that, and that's a random variable. So when I'm writing down the likelihood function, I'm expressing it like this. I'm letting that be fixed. So that's collected data. So likelihoods seem to express the same relationship between parameters and data as the sampling distribution. So there's some insight there. It's almost intuitive, but that doesn't stop people from fighting about this. I don't think people fight anymore about whether or not we can use likelihoods. I think through demonstrating their utilities, people have become convinced. And probably in this class, everybody's already convinced. Sure, use likelihoods, I've seen everybody do this. But this has been controversial before. I'll bring in some quotes and listen to some really smart people banter about really silly things. So philosophy. I do the same thing. I enjoy it too. So the likelihood function just looks like that. In the IID setting, so if IID, what we can do is we can just build this up by taking the product over the sampling function for the individual elements and just take a product over the n elements that we've observed. So in the second part is the prior. So at the end of the day, what Bayesian constructs is the posterior distribution. And that's just going to be this. equal to the likelihood. I like to write it like this, but if you prefer writing it like this and throwing that thing in, as long as you're throwing in the right expression and you're using it correctly, I don't care. But you might confuse people that speak a slightly different language. So this is just going to be the integral of the likelihood times the prior, d theta. And this is a definite integral where I'm integrating over the entire space. So really, all the shape of this function is up here. So that contains the shape. So the shape of the distribution or the shape of the density. Again, when I'm just thinking about this stuff generally, I usually think about Riemannian spaces, and I'm just thinking of theta as continuous. That's how I like to think about things, because I think it's more general than thinking about things as sums. So I'm imagining theta as continuous on all this. And I haven't said too much about x, because it really didn't matter if it were discrete or continuous. So the Bayesian uses Bayes' theorem that is completely uncontroversial in this format, where they apply it directly to the likelihood function. Or you can think of this as penalizing the likelihood function. I kind of think about it all different ways. So all of those ways of thinking I think are pretty natural. But this, the way I really think about this, is this has all the connection between your data and the parameter. And so if this function tells you everything based off of the parameter, what the distribution of the data looks like, that should have information about the parameter given the data. So if I give you the data, that same mathematical form should have the information in there. I'm not sure what's controversial about that. I think it's because people like to do things that maybe they come up with procedures sometimes that if it has the same likelihood but a different sampling distribution, and that is possible. An example would be negative binomial and binomial distributions. So we'll talk about that when we see the likelihood principle. That example is in the book. But I think that it's intuitive that that mathematical expression should be used. So one of my key points in class is use likelihood functions. They're very powerful. They can be used in lots of different ways. So I tend to think if you didn't base your inference off of the likelihood function, you can be beaten. Now, there's a little bit of a fiction. I'm imagining all our analyses in this class are parametric. So you might be asking classes questions about, what if I don't know what the likelihood is, or I can't write it down? Those are all valid questions, and we're not going to cover those cases in the class. But I would say in spirit, if you have a sampling distribution, there is at least conceptually a likelihood function that's connecting all the relationships between the parameters and the data. And this is really just a penalization function. So if you want my heuristic way of thinking about this, this is just a set of control knobs for putting restrictions on theta so that we get good properties over here. That's it. So that obviates and gets rid of all the arguments about what I thought a priori. I didn't think anything a priori. Maybe I don't have any thoughts a priori. And I think that's probably the most distasteful part of Bayes, because people think you need to know something a priori. Well, what if I don't know? That just means you're riddling your analysis with your assumptions, and it's subjective. And they use all these words, and I think that's just a human thing. So really, at the end of the day, it's a question of what are you going to do with this? And does it really express uncertainty in theta based off of the data that you've seen so that you can get reliable estimates or coverage intervals or credible intervals or however you want to think about those intervals? So that's the name of the game. So I just see this as a set of control knobs. I do agree that if I did know lots of things about theta, I could encode it here. So if I did have subjective knowledge about theta, so what I mean by subjective knowledge is experiments have been run before. Why would we call that subjective and not objective? They're just words. So one sounds more appealing than others. And I think this is just mind trickery. So, but if I did have other experiments telling me things about theta, I could maybe encode that into the prior. That's called a meta-analysis. So if I did have all kinds of extra studies that were run independently doing different things that they told me about thetas, I could use this as a sequential updating scheme. And some people explain Bayes that way. So this is my previous knowledge about theta. I slide through the likelihood and I update my information with posterior distribution. And that's where the lingo comes from. It doesn't mean you have to do it that way. There's other ways of thinking about things. I will say sometimes I'm an objective Bayesian, but only subjectively so, because I picked my criterions. So I picked the criterion that I'm trying to optimize, and that's called choice. So, and I think we're always making choices. So I think everything in some sense is some form of subjectivity. Even when we build up our sampling functions, our data doesn't come with that in hand. We do some modeling and we make choices. So if you are going to be a subjectivist, be a compelling one that appeals to lots of people. And you might be able to pick some objective criterions that we can all agree on, maybe. Maybe that's what we want. Okay, so Bayesian just is using Bayes' theorem in this funny way. So let me just tell you a definition on conjugacy. So a prior is conjugate. Be careful with this word. It is used all over mathematics, and I can't make a connection half the time between the different usages of the word. So if you take a complex analysis class, I'm not talking about anything like that. So I'm not talking about taking the conjugate of a matrix or something like that. So this just is an entirely different usage of the word than maybe you've seen before. So a prior is a conjugate if, so I'll give this a name, a prior pi theta is conjugate if pi theta, so this is just the if statement, is an element of F. And we're going to call F a family of distributions. So what I mean when I say family of distributions, I mean something like a normal. So usually we write something like this down, pi mu sigma squared right here. So there's two parameters that tell us which normal distribution it is. So if I'm thinking about this generally, whatever this function is, we know how to write it, e to the minus quadratic form. The family is all the different possible normal distributions I can get by varying mu and sigma squared. And there's an infinite collection of those. So I don't mean the exponential family is what I'm getting at. An exponential family of distributions is a family over families. That's your big extended family that you only see twice in your life. So I'm talking about the ones that you see on the reg. So your close family. So a normal. So this would be a family of distributions. Or, here's another example, a Poisson. So, I don't mean normals and Poissons. I mean it's either one or the other. It's Poisson or a normal. So there's an infinite collection of Poissons by varying lambda. So that's a whole family of distributions. So if this is of a particular type and pi theta given x, the posterior distribution is also a member of that family. So posterior is a member of the same family. So I don't mean things like exponential distribution because I could really be changing the family class in there. I could be talking about a gamma and a normal, but I'm just specifically talking about one of them. So what I mean is if this is normal and that is normal, then we say the prior is conjugate. If this is Poisson and that is Poisson, then the prior is conjugate. If this is beta and this is gamma, it's not conjugate. That's actually impossible to do. So you can come up with a reason why the prior cannot be beta and the posterior be gamma. Does anybody know the reason off the top of their head? The support, yeah. So beta lives between 0 and 1, so I'd be chopping out all the other stuff greater than 1. So that's not even possible. So here's the then statement. Then pi theta is conjugate. So that's the idea. So we'll do an example in a second. Do a couple examples. There's no way you can do this. You cannot just stare at the prior and know if it's conjugate. If somebody says, is that a conjugate prior? I have to know what the likelihood function is to slide that thing through. Slide, i.e. multiply. So multiply it into it and notice it has the exact same form. So you have to know what the sampling distribution is, to know what the likelihood function is, know the nature of those parameters to be able to recognize what the conjugate prior is. So let's do an example. Let's do xi's come from a normal distribution with mean mu, variance sigma squared. I'm going to say this is known. So that's just constant. We're not going to do inference on sigma squared. We're just going to do inference on this. So the goal is to learn mu. And we get to observe this. And I get n data points, and yes, it's IID. So, question. What's the conjugate prior? I know some of you know this. If you've done any form of Bayes, parametric Bayes, they probably kicked it off with this example. Let's just see how we even answer this question in the first place. So what I need to do is I need to write down what the likelihood function looks like. So write down the likelihood. I'm going to express it like this. I cannot help myself. I like it just as a placeholder because if I were teaching a full-blown Bayes class, probably the next question I might ask is how do you infer sigma squared? We can look at that in a moment. It would be okay to just throw this away, but I would probably ask, if you were doing this, did you marginalize out sigma squared, or are you just not telling me that it's there? And all I'd have to do to discern the difference is look at the equation for the likelihood function. And if I saw sigma squared sitting in there, I go, oh, it's just a fixed constant. You're just denoting that to me. So this is going to look like this. I goes from 1 to n, e to the minus 1/2, and if you will, I'll write this down. 2 pi, sigma down here, e to the minus 1/2, xi's minus mu squared over sigma squared. So one thing I can get rid of real quickly, because likelihoods are just expressing the shape in the parameter of interest, and the parameter of interest right here is mu. So that's our theta. So that's my general parameter that I want to understand, but this is a specific parameter, probability distribution. So I encode it like that. I can get rid of all this stuff if I want to. Keep in mind, if you didn't know sigma and you got rid of that, you just made a huge mistake. But if it's constant, it just gets soaked up in the proportionality. So I'm not estimating it. And so all I need to do is write down this function right here. And so I might figure out real quickly that this function is just expressed is e to the minus some quadratic form in mu. So this looks like this. E to the minus quadratic form in mu. And if you prefer, I'll put the half down there. And I'll soak the sigma into there. So quadratic form. I'm just going to make a bold statement right now. And we will demonstrate this. You're certain to do this. If you haven't already done this, I guess we might as well just glance at it right now. But I just want to point out that this thing right here, e to the minus 1/2 xi minus mu squared over sigma squared is proportional to e to the minus 1/2 x bar minus mu squared sigma squared over n. And all we need to do is just expand it and show that they're proportional to each other. So they're off by a normalizing constant. So we can just do that real quick. E to the minus 1/2, I'm going to drag my product into the sum of the exponent. I'm going to expand the square, xi squared minus 2 mu xi plus mu squared divided by sigma squared. I'll drag the sum through. E to the minus 1/2 sum of the xi squared over sigma squared minus 2 mu, this is sum of the xi's, over some sigma squared, plus, and I'll just sum up all of these constant terms right here. It's going to be n times mu squared over sigma squared. So I'm just taking that sum and summing up this constant time n times. And if we end up expanding this thing, we come up with something similar. It's different, but it's very similar, and it has the same shape. So this is going to be e to the minus 1/2. There's no sums in here per se. So this is x bar squared over sigma squared over n minus 2 mu x bar sigma squared over n, excuse me, mu squared over sigma squared over n. And so one thing you can do is you can replace this with, I'll just say n times, if I take this n and I multiply it upstairs, so n times x bar is equal to sum of the xi's. Those are exactly the same things. And so I look at this, I can factorize this thing out of the exponent. So this is a constant with respect to mu. This is a constant with respect to mu. They're similar, but they're different, is the point. So that part's different, but they just factorize out, and they get absorbed into the normalizing constants. So if I look at this term right here, that term appears right here. Those are exactly the same. I'm just pulling the n up here, and this term looks just like this. So if I ended up graphing those, they would look exactly the same. I'm just going to point out real quickly, because we can do this, and we're observing this, I notice that I can never untangle mu from that thing, x bar, or some of the xi's. I'm just going to make a bold statement. That means that it's the sufficient statistic. Because I can't compress that down any further in terms of dimensionality. That's a one-dimensional thing. That's the smallest size sufficient statistic that I can have for learning what mu is. So all the information about mu is buried into the likelihood function. So regardless of how I encode this, it's got the same likelihood function. So I like using this form a little bit more with x bar. And I like using that form even more when I hit a computer, because I don't have to sum up xi's every time through a loop. So it saves storage, it saves computational stuff, and it's a cool mathematical idea. We're going to touch on that mathematical idea later this week. Okay, so back to our question, what's the conjugate prior for all of this? I've got e to the minus quadratic form in mu squared. So this thing. And I've written down two forms that are equivalent to each other. So the question is which prior can I multiply in terms of mu that I preserve the form of the prior. And I'm just going to make a statement about it, because I don't know how to do it other than just recognize things and to know things. So if you don't know your distributions and properties of your distributions, you can't get any of these problems. So I'm only going to ask you questions about distributions that we touch in this class. Things like normals and Bernoullis and binomials and Poissons. So here's the idea. So what's the conjugate prior? It turns out pi mu has to be some other normal. And I'm going to give it its own parameterization. These things are called hyperparameters. People seem to like this word a lot. Good job, statisticians, finally coming up with a word that people like. So, if it would have been like most statisticians naming things, they would have called these parameters that underlie your prior distribution. And that's it. So these are params that I'll just say are in your prior. So that's the language. And I ask that all the time. What are your hyperparameters? So I don't have a problem with the functional form you're using. I want to know how you picked them and why you picked them. And if somebody says it doesn't really matter, I'll say demonstrate that. Because I don't believe you. So they need to be able to demonstrate that if they wiggle these things around, I get about the same sort of inference. Okay, let's just see that this is true. So, pi mu, given x, I can't help myself on writing down sigma squared, telling me all the things that I'm holding to the side for maybe a more realistic analysis. This is going to be proportional to e to the minus 1/2 x bar minus mu squared over sigma squared over n times e to the minus 1/2 by distribution is over mu. It's centered here, and that's the variance of that distribution. So this is going to be mu minus mu naught squared over, I'll say sigma naught squared. So these are not necessarily the same things. Now, I probably, if you told me what sigma squared was, I'd probably use that to express my prior. So I might be able to say, oh, I want my prior to have a certain amount of weight. So if I just use sigma squared in there, I'd be letting my prior act like one additional data point in the analysis. So this is e to the minus quadratic form. And this is e to the minus quadratic. Having a hard time spelling this morning. I'll just go with a lot. So e to the minus quadratic, and this is in mu. And this is in mu. These aren't exactly the same function, so I'll call them 1 and 2. But if I add two quadratics together, what do I get back? A quadratic. So that's always true. So when you see e to the minus quadratic form, that's a normal distribution. So this is going to be e to the minus q1 mu plus q2 mu. If you want to put the 1/2s in there, you can do that. So 1/2, 1/2, I'll put the 1/2 in here. And so this thing will look like e to the minus 1/2 in some other quadratic, and I'll call it q3. And you can figure out what that quadratic is. And that would be the name of the game for identifying which normal distribution this is. So what that means is that this is normal, that's normal, the posterior distribution, so the prior is constant. It's that simple. So you have to use your imagination. I'm always mentally multiplying things through and seeing what preserves the form. And after a while, if you know all your distributions, you can spot it real quickly. Let's do one more. We'll come back to this example. I know I'm just kind of rushing and giving you the idea. You'll get to work through that example in homework. So one more example. This was the example that we were talking about last time that we're going to base our simulation study on. Xi is, I'll say Bernoulli. P. I goes from 1 to n. Yes, everything is I. So just flipping coins. Same coin every single time, coin's not changing. P's not changing, same P. So let's just write this down. Our likelihood function on P looks like this. Product I goes from 1 to n, Pxi, 1 minus P, 1 minus Xi. I should probably tell you that I have these encoded as ones and zeros, where this happens with probability P, and this happens with probability 1 minus P. Basic stuff. So this is what the likelihood function looks like. So I want to just point out this thing right here. When I plug a 1 in for this, that disappears. That's just a 1, because that's a 0, and this is P. So when X is 0, that's 0. This thing becomes a 1. That's 0, that's a 1, so this is just 1 minus P. So this is just a way of encoding that probability statement for Bernoulli by just building in this switch. So an indicator function, and I'm just switching everything on and off. So this looks like this. P to the sum of the xi's, 1 minus P, n minus sum of the xi's. And the question is can you recognize what I could multiply this thing through and preserve its form? And the hints are littered in that function and in all of your textbooks that tell you what distributions are. I just want to point out one more thing since we're here. This is also true. Note, I'll say X, let's just let X be sum of the xi's, i.e. X is just this. So I'm kind of abusing my notation right here. If you want to call it sum of the xi's and that makes you feel better, do that. So binomial with parameter P, and usually they put an n in here as well. I need to tell you what n is, how many times I flip the coin, so I can talk about the number of successes. And f of x is this. Sum, I'll say, actually, let's just forget that. I want the formulas to look like you've seen before, so let's just get rid of that. I'll just talk about the sum of the xi's. So that's just a random variable. I'd probably call it something different without an operator, but we can just think about it as the sum of the xi's. This is going to be n choose sum of the xi's. P to the sum of the xi's. 1 minus P, the n minus sum of the xi's. And I think we all know that. So these are all ones and zeros that I can put in there. These are the number of ways that I can rearrange the ones and zeros. So I want to point out that this is proportional to this. So this thing is all just a constant. It doesn't have any p's in here. So this function has the exact same shape as this. It's just raised up. So they have the exact same likelihoods, and that's why I keep saying it doesn't matter if you think of this as binomial or Bernoulli, because they're the same exact likelihood functions. So the question is which distribution is this? Which distribution can I multiply through and preserve that distribution? That's what I mean to say. And I'll just write down the answer. beta. It's not a specific beta, it's a general beta. And so, if I plugged in actual hard numbers right here and I didn't get back those hard numbers in the posterior distribution, that would be a different distribution. And so I let these just be variables. So beta looks like this. FP, given alpha and beta, these are the hyperparameters. This looks like this. P to the alpha minus 1, 1 minus P to the beta minus 1. If you want to know what the normalizing constants are, it's the inverse of a beta function. And I'm going to talk about this slowly next time. So this is beta, different beta than that beta, alpha beta, inverse. So I want to slow down and talk about this function very slowly, because I just said beta 3 times and I meant something different every single time. This is a beta distribution. This is the kernel of a beta distribution right here. It looks just like this thing. You can mentally probably do the multiplication and see that it preserves the form. This has a hyperparameter beta in there. So I've got all these different betas and I mean something different every single time. Beta function, beta kernel, beta hyperparameter, all different things. So I want to talk about this distribution and have us visualize what it looks like. But you do the mental arithmetic and just show that if I multiply that function by this other function, I come back to something that looks just like another beta. And so that means that the conjugate prior for this is beta. I'm going to say that all over again next time, and then we're going to simulate it and see what this actually looks like for the Bayesian. So this is the prior that we'll focus on, and I will point out again, if I make this a 1 right here, that becomes a 0. So this becomes a 1. If I make that a 1, this becomes a 0, that becomes a 1, and it has no shape. Or I should say the shape is flat. I guess that is a shape. So it flattens everything out, and that's a uniform distribution. I'll also point out P belongs to 0, 1 in this form, so these model probabilities. Let's slow that way down. Come back next time, see what this posterior is actually telling us, and see if it's even a good idea in the first place to do an analysis this way. I'll give you the punchline. It works out really great. So.